Hey folks, how we doing? Here we are, our final unit of ninth grade science. Pretty amazing how far we've come and the strange circumstances that we have faced along the way. One real quick thing, I am going to open up the exam if you would like to do a retake. You'll have one opportunity at that, and that is an option. Again, it is open note, but but not open pre practice tests. So, hope that helps. If things didn't go quite as well as you had intended or hoped and dreamed, but I think that should be plenty fair, and hopefully we get some great scores. So far, they've been looking good. So today we're going to start our next unit. Our next unit is about forces and motion and moving objects. And today we're going to talk about a couple of real key concepts that are involved with that. Speed and velocity, and you'll hear some terms like distance and displacement, and get to do a little math along the way. The questions that we were hoping to answer, again, what's the difference between these terms distance and displacement? What's the difference between speed and velocity? We usually use those terms interchangeably, but there is an important distinction. And how do you calculate these things? And then one other term that we'll introduce to you is called, what is instantaneous speed? When we talk about moving objects, we talk about the motion relative to, we think of things standing still. We need some sort of frame of reference, okay, in terms of taking the context of that. You can make the argument that, well, here we are, we're on planet Earth, which is zooming around the sun, and we're spinning around in the process as well. So we're all in constant motion, but relative to each other, that's the motion, of course, we're referring to. If you're moving side by side with someone who's going the exact same speed, the exact same direction, it may appear that they're not moving at all, and so forth. So that's what we mean by a frame of reference. So relative motion is going to be the motion in relation to some sort of frame of reference. Today we're going to learn about a little distinction between what we call distance, which is the total distance that something is going to travel, okay? And we'll be using the meter for our unit of measurement. And displacement, which is really kind of a straight line between point A and point B. Here you see a little diagram. The total distance traveled, if you don't go in a straight line, is going to be that dotted line. You can meander all kinds of different places. The displacement is going to be the direct line between points A and B. And so if you go around in a circle, your displacement technically is zero, even though clearly you run around a track, obviously you traveled some distance. Here's a little diagram about Alan and Eva, and they are going to travel from the west gate to the east gate. And you notice Eva takes the nice direct path, shortest distance between 2 points, while Alan is meandering around. All right. In the end, they both get to the same place. Their displacement is identical. The distance traveled, however, Alan's path is quite a bit more. Sometimes we like to graph distance and displacement, and the time component then comes into play, because we want to tell, well, how much distance are we traveling over time? You see the blue line there is showing a fast, constant speed. Notice the line is nice and straight. The red line shows a gradual slope. You're continuing to increase distance as the time goes on, but notice how the slope gets greater and greater as you go. That has something to do with what we call acceleration, which we'll be getting into later on this week. And then the orange graph is kind of tracking displacement. Here is as if someone starts heading off in a direction and then stops, hangs out for a while. They're stationary. And then they start walking back to where they came from. And so the displacement ends up being zero. Now, speed, of course, is something that we'll be paying close attention to as we move, and has to do with, what is that distance that gets traveled over a period of time. We'll be measuring things in meters per second here in the science lab, and things move at far different speeds depending on what you're measuring. Maybe you've heard of Usain Bolt. Usain Bolt is recognized as the fastest man in the world. He has world records in both the 100 meters and the 200 meters. And here's how Usain stacks up with some other things. Notice all relative. Usain is fast, but he's nothing compared to the cheetah. Can't keep up with the gray wolf either. Average bike rider, 10 miles per hour rather. Michael Phelps, greatest swimmer in the history of the Olympics. There you see his speed, and then just average walking, how they all compare. Distance traveled over time. Now, velocity has a slight distinction. Velocity is speed, but it's in a particular direction. It's got a directional component to it. And so that will change it. It's actually a vector measurement. We're not going to get into vectors that much, but it has a direction component attached to it. Sometimes we'll talk about instantaneous speed or instantaneous velocity. If you look at that little graph there, you'll see it's as if, someone started out, and we don't necessarily go the same speed the whole time. Sometimes we accelerate and then we slow down. That's what it's trying to indicate there. And that at any given point on that graph, that would be indicative of our instantaneous velocity. Now, we do have a very important formula to use, and that's going to be, it's really the same formula for both speed and velocity, but it's going to be an average speed, an average velocity. And you see it's going to be v is equal to d over t, or total distance divided by the total time. Got that little triangle there to help you as well, because as we'll see, that formula really can be three formulas in one. The units we'll use for speed are going to be meters per second, distance we'll measure in meters, and time we'll measure in seconds. Little sample problem. If Mr. Call, when he gets hungry for lunch, takes 20 seconds to travel from his room to the science teacher's lounge, which is 30 meters away, what is Mr. Call's velocity in meters per second? Well, first thing we want to do is we want to fill in. We got those three unknowns there, v, d, and t. Let's take a look at what we are given in the problem. We know we want to know the velocity. V is what we're looking for. We know the distance is 30 meters. We know the time is 20 seconds. So if I take my formula and I start plugging things in, I know v is equal to d over t. Distance is 30 meters, time is 20 seconds, and when I do my math, 30 divided by 20 gives me 1.5 meters per second. Now, as we mentioned, that formula can be written different ways, can be used different ways. In this problem, a girl on her ATV has a top speed of 30 meters per second. How far can she travel in a minute, or 60 seconds? Well, once again, let's look at we got v, d, and t is what we're looking for and trying to figure out a formula. In this problem, it gives us that the velocity is 30 meters per second. The distance is what we're looking for in this problem. How far can she travel? And the time is going to be 60 seconds. So when I do my math, set it up, velocity is equal to distance over time. Okay, there's my 30 meters per second is equal to my distance, which I don't know, divided by my seconds. All right. Well, to solve that, when we got that 60 seconds down in the denominator, kind of not something we want to work with. We want to get rid of that. So we're going to multiply both sides by 60 seconds. That'll cancel out the 60 seconds on the one side of the equation and just leave our unknown distance over there. And if we multiply by 60 seconds, you'll see that it is cancels out the seconds in the unit of 30 meters per second on the left side. So now when I plug things in, I'm left with 60 times 30. 1,800 meters would be my answer. Back to Usain Bolt, ran the 200 meters at 10.4 meters per second. How long did it take him to run 200 meters? Well, and again, you might say, well, Mr. Call, didn't we just look at that he was traveling 27 miles per hour? Well, remember, in a race like that, you're starting out at a time zero. You're not traveling that speed right from the get-go. So we know that he's traveling average speed of 10.4 meters per second. We know the distance is 200 meters. The time is what we're looking for in this problem. So once again, we set up our equation. Velocity is equal to distance over time. 10.4 meters per second is equal to 200 divided by whatever the time is. And once again, we don't like that in our denominator, so we're going to multiply both sides by time. It'll cancel out on the right side of the equation. Now time times 10.4 meters per second is equal to 200 meters. And when I do my math, now I'm going to figure out time, I'm going to have to divide both sides by 10.4. I get 200 divided by 10.4 gives me 19.2 seconds. All right, so quick recap. Distance and displacement are distinguished between the total distance, total meters traveled in distance, and displacement, of course, is going to be the direct line between points A and B. Velocity is going to be speed, but with a direction component attached to it. That's what distinguishes those two together, or from each other. And then we've got our formula. V equals d over t, distance divided by time. And instantaneous speed would be any moment in time where you take the speed based on that graph. Take your quick quiz, and we'll be back tomorrow.